Today, we are diving deep into one of the most incredible, yet totally overlooked processes our bodies perform every single day: healing. It's this silent, microscopic ballet of mind-boggling complexity, and we're about to pull back the curtain and see how the magic happens. I mean, seriously, what is going on under the surface when you get a simple cut? It's way more than just slapping on a Band-Aid. The molecular story that unfolds is more dramatic and coordinated than you could ever imagine.
So here's our game plan for this explainer. We're going to break this whole thing down like a biological symphony in 5 parts. We'll start with the initial alarm, move through the rebuilding, all the way to the final touches, and then we'll look at what happens when the music just stops.
Okay, so to really get wound healing, you have to stop thinking of it as just one thing. It's not. It's more like a biological orchestra. It's this amazing performance with millions of tiny musicians. We're talking cells, proteins, genes, and they're all following a super precise musical score to bring everything back into harmony.
And the scale of this thing is just massive. We are not just patching a hole here. This is a full-blown cascade that involves cells talking to each other, tearing down and rebuilding the very scaffold of our tissues, regulating the immune system, and even calling in stem cells as backup. It's a huge, huge undertaking.
All right, that brings us to the first movement, the immediate chaos right after an injury. This is the dramatic opening, you know? It's all about speed and action. The body's #1 priority is to control the damage and sound the alarm, loud and clear.
And the response is practically instant. We're talking within seconds of an injury. The orchestra hits its first urgent chord. Platelets just flood the scene. A coagulation cascade kicks off, and a fibrin clot starts forming right away. And this clot isn't just a plug to stop the bleeding. It's also the temporary stage where all the real repair work is about to begin.
You can think of these platelets as the conductors of this whole opening act. They show up and immediately start releasing this chemical cocktail of signals. Each one has a very specific job. One signal, PDGF, is basically shouting, "Get the construction workers, the fibroblasts, over here." Another one, THGF-beta, activates the cleanup crew. A third one, VEGF, starts the process of laying down new plumbing. That's the blood vessels. And a fourth, EGF, literally wakes up the skin cells, telling them, "Hey, get ready to close this gap."
Now, for the next day or two, the wound is basically a war zone, dominated by one key player, the neutrophils. These are the immune system's shock troops. Think of them as the security team that swarms the area. Their job is to rush in, sterilize everything with powerful chemicals, and just clear out any invading bacteria or debris. Yeah, it's messy, but it is absolutely essential to stop an infection.
And this right here, this is one of the most critical moments in the entire process. After that security team does its job, the music has to change. The aggressive, pro-inflammatory macrophages, the ones in decontamination mode, they have to switch their personality. They need to transform into pro-healing macrophages. This shift from loud war drums to a calm, constructive melody is non-negotiable. If this switch fails, the wound gets stuck, and that's when things can turn chronic.
Okay, so the site is secure. The emergency is over. Now, the orchestra's tempo totally shifts. We're entering the second movement, proliferation. The frantic alarm bells fade out, and they're replaced by the steady, rhythmic sounds of construction. The rebuilding crew is on site.
So how does your body actually close the hole in your skin? Well, it starts with the surface cells, these keratinocytes. As soon as they get the signal, they completely change their internal programming. They go from being stationary bricks in a wall to becoming these mobile workers that literally crawl across that fibrin scaffold we talked about until they meet up in the middle and form a brand new top layer. It's amazing.
Meanwhile, underneath that new surface, the real heavy lifting is getting started. And the foreman of this whole construction project is a growth factor called TGF-beta1. You could call it the master signal. It's the one telling the main construction cells, the fibroblasts, to get to work and start producing the new structural matrix.
But of course, no construction site can run without utilities, right? Same thing for a healing wound. In a process called angiogenesis, the body starts building brand new blood vessels to get oxygen and nutrients to the site. And it's a total team effort. One molecule, VEG, is the main driver. It basically says, go. Another one, FGF2, acts like an accelerator, speeding things up. And then a third, PDGF, comes in at the end to stabilize the newly built pipes, making sure they're strong and ready to work. And now we are entering the final grand movement of this whole symphony. This is the remodeling phase. And let me tell you, this is the longest part of the performance. We're talking months, sometimes even years. It's all about taking that structure that was built in a hurry and carefully refining it, making it strong for the long haul.
A really crucial part of this is something I call the Great Collagen Switch. See, the first matrix that the fibroblasts lay down is made of a weaker, messier collagen, type 3. You can think of it like temporary wooden scaffolding. Then, a demolition crew of enzymes called MMPs comes in and tears it all down. Why? To make room for a much stronger, more organized type I collagen. That's the structural steel. This switch is what ultimately gives a scar its final strength.
Now, during this remodeling phase, some of those fibroblast construction workers get a promotion. They turn into these specialized cells called myofibroblasts, and they have these little contractile fibers, almost like tiny muscles. Their job is to physically pull the edges of the wound closer together, tightening up the final structure. But here's the catch. If these cells don't get the signal to, disappear when their job is done, they just keep pulling. And that can lead to those thick, raised scars.
So now we've reached the end, the coda. And this is really the why this all matters part. What actually happens when this beautiful symphony just grinds to a halt? And, maybe more importantly, how is modern science learning to pick up the conductor's baton and get the music started again?
When you see a chronic wound, like in patients with diabetes, what you're really seeing is an orchestra stuck on a single destructive note. The molecular reasons are pretty clear. You've got way too many of those demolition enzymes. The inflammation never shuts off. The blood supply is failing. And bacteria can even build these protective shields called biofilms that just mess up the whole performance.
But this is where it gets really exciting. Because we understand the musical score now, we're figuring out how to hack the orchestra. We can add in missing conductors using growth factor therapies. We can bring in new, super versatile musicians with stem cells. We're even learning how to rewrite the music itself using gene therapy. We're finding ways to quiet down those overly destructive instruments and even retune the cells so they perform better. It's incredible stuff.
And this quote from the source material just wraps it all up perfectly. It's not one thing. It is a beautiful, deeply integrated performance. Everything from growth factors to these complex cytokine networks and even bioelectrical signals, every single part has to play in perfect harmony.
And that leaves us with a pretty fascinating final thought to chew on. We're moving way beyond just patching up wounds. We're now on the verge of actively directing regeneration. So the big question is, if we can learn to conduct this orchestra to heal a wound, what other symphonies of regeneration could we compose in the future? Thanks so much for tuning in.